Join us for an enlightening session of Taming Monsters with Dragons, or How to Build Digital Teams the Right Way, where Robert Karban and István Ráth guide us through the evolution of system engineering. They will address the challenges posed by the complexity of modern systems across critical sectors and the shift towards disturbed teamwork that complicates collaboration. First up is Robert Karban.
Okay, hello everyone, I'm Robert. And I'm gonna talk to you for the next 19 minutes and 30 seconds. So, many years ago I presented at another conference. It was in Singapore, and they sent out a message to the presenters the day before I was on stage, and they said every presenter is required to wear a shirt, right? And I'm not much of a shirt guy. Anyway, I have a shirt like today, coincidence. And then I went on stage, started my presentation, and at some point I took off my shirt, right? And put it on the side. And guess what happened? Nothing happened. Nobody cared if I wore a shirt or not. So there was a requirement, and the requirements are very important in system engineering, so we'll hear a little bit about that today as well. But it's important that someone verifies and qualifies that requirement from the very beginning towards the end, right? So the conference, in the end, like today, I guess, but there was no such requirement, so we're fine. The presentation is called Taming Monsters with Dragons, or How to Build the Digital Twins the Right Way. Who knows what a digital twin is? Cannot see anything. You think you know, huh? Yeah, let's see if that's true. Okay, so I'm going to talk a bit. So I worked the last 10 years at the Jet Propulsion Lab in California. So I just flew in for you here today. No, that's a lie. And so and there's a lot of system engineering going on at JPL. So there's one division which is around 1,000 people, right? And the definition that we have, or JPL has, is that system engineers guide the concurrent collaborative design of complex technical systems, right? That's kind of the headline, what a system engineer is doing, right? And that basically consists of three things, right? Leadership, right? And I think there is where the Americans are far ahead of us Europeans, right? Because we have what I see here coming back after this 10 years, a big lack of people do something about that. In particular, the ladies, right? I heard someone told me there are 14% of women in STEM, but here, ladies, make some noise for a second. Where are the ladies here? Hello? Okay, you have to become much more. Huh? You cannot leave the field to the guys. That's just not a possibility, right? I had on my team at JPL, I had 80% women. The best. And leadership. The second part is the architecture and design of cyber-physical systems, right? Because everything nowadays is kind of software defined, be it cars, mobile phone, or spacecraft. And then we have to manage that complexity, right? Sounds very simple. And actually, if you look at, so that's from one standard, what the systems development process could look like. I will not go into details, but basically, you develop some requirements, you do some design of architecture, you evaluate the architecture and design, you synthesize, and you do loop a little bit around, and then there you go, you have your system. If it was only so easy, but it's not. And why is that not? Because usually there's a lot of people involved, right? So that's the team of Perseverance. So that's the rover that is currently, the last rover that is driving around on Mars, right? And lots of people work on the project, right? And unfortunately, nowadays still a lot of system engineering is done with Excel. Not good. So, and on top of that, not only is it on Excel, but with PowerPoint and sending emails around with PowerPoints and Excel, right? And then at some point you have a huge mess. And then only with heroic effort you can do something like that, right? You can actually land on Mars, right? Or fly on Mars, right? So how? And that is very, very challenging, right? You can imagine these are complex missions on another planet. And so how do we get from that to that, right? So there's a huge gap, right? So what we're trying to do is to bridge that gap, right, as engineers. So what is the problem of engineering today, mostly of system engineering, right? There's a very bad ratio of real engineering, right, and basically what the janitor does, the overhead, right? So you have to over and over again enter the same data in different places. You have to find the right version of the data, right? And you have to constantly look for it, right? Where is the right thing? Who is owning it? I don't want to re-enter it every day, right? So those are the kind of three elements that makes it very, very challenging today, right? On top of that, we have all those that increasing complexity, in particular of spacecraft, but any kind of system nowadays, right? There's more functions, there's more hardware, there's more software, and even more software, right? Why is there so much software nowadays? Right? And what you observe is that silos occur, right? There's different kind of silos across disciplines, across products, in the same project, between teams, and so on, right? Those are the monsters, right, that we have to kill, right? So here's an example of flight software, the ground data system, remote engineering unit, right? There is a system engineering process, but still those silos occur, right? And they do their thing individually, right? But the problem is that they live in some discontinuous space. So there is an overhead. They all have some connection that is not explicit, right? So we have an overhead, a huge overhead to connect all those things, and usually that is done manually, right? But we have to break up these silos to get a consistent system and not to have all this confusion during the engineering and system development process, right? Those are disconnected, and a lot of pain comes because Excel is so easy to use, right? That's really the bottom line, basically. And the qualification process does not work systematically. And qualification means like the verification validation, not only at the end when you have already the piece of hardware, but also from the early stage on of your development, right? Right on when you evaluate different architectures. So that has to start early. So it's really hard to understand those relationships of those things in those silos, right? How, for example, to check requirements against the test, right? Sometimes you have to verify the requirement, and just that traceability, that the requirement has been verified, when, by whom, how often, did it fail, did it pass, whatever, right? That's difficult in a way that it is auditable, right? Someone comes in and we can demonstrate actually it has been done and has been done properly, and it's repeatable, right? And even more problematic is if something changes, right? So what's the impact of that change? Be it something the design, be it something the code, be it something the requirements, right? We wanna be able to perform an impact analysis. If I introduce a change, what is affected by that change in the whole spectrum of the system development, right, wherever I am. But also I want to be able, once I have done this analysis, I want to be sure that I actually can trace that impact and make the change in like a configuration managed way, that I know where I made changes because in all these products because something changed from the top and propagated down the line, right? So, but what we claim is that all those monsters, they can be resolved by using models, right, to capture those relationships, right? So we are moving gradually for the last 20 years towards a model-based approach in system engineering. In other disciplines, models have been around longer and be more like kind of used already than systems. Systems is more new. So how do we connect all these things together, right? So in this colorful slide, there's kind of three things. You have a systems development iterations, right? So this is basically the the spiral as you go along in your systems development, and you have certain milestones where you deliver something. But we have corresponding digital twins, right? And these digital twins, they're represented by this fractal structure here. And the fractal structure basically represents that as we go along in our system development, they become higher and higher fidelity, right? Until we know enough that we can build that system, right? So we progress towards that implementation from the early start on, from the early phase of the development, towards we have enough information that we can build this system. So the qualification of that, and they are all tied together. You see this red thread here, right? So you can only move from one version of a digital twin to the next one, the first one, the previous one is qualified, right? And as you go along, the previous ones always have to be validated and qualified. They always have to be valid. That's the vision, right? So we want to have this red thread through the whole systems development life cycle, right? And this is what we call dragon. And now comes the dragon that eats the monsters. So we want to have a formal qualification of systems modeling and software, right? Today what we see and observe is a gap between system engineering and software engineering, control systems and so on. So there's kind of an engineering gap that has to be integrated. But we want to formally qualify our system along the life cycle, right? We want to have a repeatable, executable representation of the system, starting very early on in some very abstract terms and becoming more and more concrete and with higher fidelity as we go along, right? Different levels of fidelity. We want to have an explicit qualification record, right? We kind of come in at every point in time and say, okay, this is how we qualified up to now our system, right? With analysis, with tests, and we have traceable across all the artifacts. And we have the relationships between those representations. And that results in a systematic process for developing our system. Right? So as we go along, we need different engineering environments, as we call it. So that's all the collection of engineering applications and services to support requirements development, to perform architecture and design, to develop your code and your hardware, whatever, right? So the engineering environment will change. Different parts of the engineering environment will be used along that life cycle, right? But they all will be valid along that time, right? So that's what you kind of see here. There's somehow indicated different versions of the engineering environment that support different versions of those pipelines, digital twin pipelines. So here's an example for those, that I found actually recently. AUTOSAR is a standard for automotive, and there is in the standard there is this text fragment here that describes how some frontlight manager should work. The details are not important really, but there's a lot of shell statements. It's all text, right? So those are textual requirements. And then I made the effort to transform it into some model, right, which is a state machine model on the left side or the right side, on the other side. And by doing that, I already found a bunch of problems in the text, inconsistencies, gaps, and whatsoever, right? So how do you want to do that with the text, right? So that's one of our problems that we want to resolve, right? So a lot of ambiguity, implicit connections comes because we write some text description of our system, what it should do, or even worse, how it should behave, how we design it, right? But it's really hard to validate, right? I cannot simulate or execute or analyze that easily, if at all, but I can do it with that, right? Another example is a project I worked on. So I worked a long time on the biggest telescopes developing control systems. Very large telescope, extremely large telescope. They're all large in some sense. There was also an overwhelmingly large telescope in between. So there we took on the 30-meter telescope, we took an approach that was also model-driven on the system side. And I just ran quickly through that. But basically what you see here is a kind of the impact. We would change some requirement, right, for a certain engineering scenario, how long it might take, and that propagates like to an update cycle of the requirements. We would perform an analysis of our logical design that includes behavior. There's a lot of timing requirements, how long it would take, for example, to get a star into the field of view. Right? We'll evaluate that, and we would automatically get some result that says, do we satisfy still this requirement with our as-designed system? And then we would do the same for the physical design, right? Which analyzes different parts, and in the end we will produce engineering documents automatically, right? So the whole life cycle is model driven, right? And the engineering documents that come out, be it in interface control documents, requirements documents, design descriptions, whatever have you, would be backed up by a model, right? And we would have the traceability along those lines. Here's another example that kind of matches and mixes like a system model that you see in some textual format, where you would describe like some basic architecture of your rover, for example. Then you would move into the multiphysics domain. And in this case, it's a Modelica model. You should look at that as well. And then you would have some engineering document. In this case, it would be on a wiki like Confluence, right? You would generate it there, where people can look at it, right? And over time, we would increase the fidelity of those models depending of what we want to analyze and what we want to capture, right? That's very important always, the scope of the modeling effort. We would be able to perform some quantitative analysis, right? We would have some baseline analysis, we would add new components in, we would swap some components, right? And every time we do that, we would perform an analysis to see if our constraints are still met that we have, right? And that's a model, that's like 30 lines in Modelica to have a multiphysics simulation, co-simulation of the rover, right? So very, very simple. And you can do all kinds of sophisticated simulations, right? So like surface models that you would import where the rover runs over some rock, right? Or the helicopter flies over the rover, right? So you can capture all that. And on this very colorful slide, this is kind of what all that backs up. Is the OpenMBE is one, you can look it up, openmbe.org is an open source community for model-based engineering environments. And we have, and I'm a co-founder of that, and we have developed something that is the Dragon, called the Dragon architecture, right? It's this, and what you see is a kind of a notional flow of a number of applications and services that are not representative in any way, right? But they just produce certain artifacts like requirements, design documents, executable models that you analyze, you produce some code, you perform some analysis, you produce your documents and so on, and you have some repository with what we call a formal change packets management. And then you have a global traceability across all these things. So we know when we change something, how those artifacts that we produce along the life cycle, how they are interrelated, right? We make all these relations explicit instead of being implicit and hidden in some documents. So in conclusion, what do we want to achieve, right? We want to, and this is important, traditionally the system engineering is driven very, very much, the engineering is happening through writing documents, right? So to understand the design, whatever, you have to read a stack of documents, and they're probably inconsistent and incomplete and hard to analyze. We want to shift with model-based system engineering from that document-driven, and it's not even document-driven, it's engineering through documents, it's even worse. Shift it to languages, formal languages, right? And automation, right? So all this, that's why it's called digital twin pipelines, right? Every time in this Dragon architecture, we have some requirement that flows down into architecture design through all these applications and services, and that's the pipeline, right? And they are at different levels of fidelity, right? So we want to emphasize that automation. A lot of things happen manually today. We want to automate all these things as much as possible, right? We want to have a systematic qualification and an audit trail, right? So we can demonstrate that we actually did that. We want to close the gap between engineering documents and the models, which is there. We want to break up those silos with digital twin pipelines. And we want to have everything based on standards and as a commodity, right? Here we go, 000, just in time. Thank you very much for your attention. So, and now I have to find which one I have to stand. Is that the right place?
No,
this one?
Yes, thank you. So first up, could you tell us a little bit about your work and what you do?
So my origin is in computer science in my childhood, basically. And then I spent most of my career spent on developing highly distributed control system for large scientific facilities. So I worked at the particle physics lab at CERN in Geneva. I worked at the observatories, the biggest observatories in the world, and I worked at the Jet Propulsion Lab. In the Jet Propulsion Lab, my main task was leading the team that provides the engineering environment, right, the ecosystem, the engineering ecosystem to the, let's say, 4,000 engineers that are there.
Thank you. Do you model mechanical component system as well? If you so, how do you model a mechanical subsystem of a jet engine, for example?
Can you repeat that a little bit slower?
Sorry. So do you model mechanical components and systems as well?
Yeah, so that has been a debate for many years, right? Because traditionally, mechanical engineers have had already models for a long time, right? And there's still this kind of thing, okay, we have to make our CAD model, our MCAD models. Why do we need a system model? No? So there's this kind of fight that mechanical engineers think, we don't need system models, right? But that is a mistake. So they have to be integrated. So the thing is that at the system level, we have to have defined architecture and look at different architectural solutions. There's a whole architectural solution space that we have to explore. That has to be integrated and flow down into the detailed mechanical design in the end, right? But with the complexity of the systems that we have, we need both, right? Originally, everything was very mechanical, but with the huge, let's say, emphasis or growth of software in whatever you look at, right? So every one of you learn Python is my recommendation. Well, if you don't know yet, take a class. Every engineer should know Python, in my opinion. But that's the thing. They have to be integrated, and they have to coexist and work together.
Thank you. And what aspects of documentation do you think are the most important?
That's a very interesting question. So the documentation, in the sense, traditionally, is that you have a text document, right? So, and that goes across from requirements to design, whatever, right? What we want to have is that will not go away, right? So I was running around 20 years ago, giving talks, the documents will disappear. They won't, right? As much as Excel will never disappear. So we just have to embrace that. If you cannot fight it, you have to embrace it. And how we embrace it is that we build models and generate the documentation out of it. They just become views of our engineering artifact, right? Nowadays, most of the problem is that we don't have an explicit, at system level, not an explicit engineering artifact, which is the documentation of what you're going to build, right? The textual description of that is some view of that where you explain how that thing works, right? But the main document for me is the model, the engineering model.
Thank you. And what do you think is holding back the widespread adoption of MBSE?
I think it's a couple of dimensions. I think definitely is a cultural thing, right? You have generations of system engineers that just used to do things in a certain way, and to move them to do something else is very difficult, right? So counting on you, guys and girls, to change that. And I think it's partially also a tooling question, right? And kind of giving there's a lot of pressure, in particular in industry, to do things very fast, right? And then you pay usually later for that. So this is always, people are very, it's like the story, I give you 50 euros now or 100 in 7 days. Most people will choose the 50, right? And here is the same, right? There's just, people are very short-sighted, in particular in some management floors, that the cost that you save now will be much higher later on. So it's a mix of different things.
Thank you very much for your answers and presentations. Let us continue the topic with Dr. Ráth István.
Okay. Bye.
I will try not to obscure the slide with my rather wide figure. So, thank you very much. It's a pleasure and an honor for me to stand here in front of you today to present at the university where my career has started, and of course it's a special honor to be presenting together with my friend and colleague Robert. And in my talk, I'm going to be giving you the second piece of this very interesting puzzle, how to build digital twins the right way. And by the way, just a starting question, having listened to Robert's presentation, I wonder who among the audience would think that tiny little piece of all the software that is used by our friends in California to make a helicopter fly on Mars is made right here in Budapest, in Hungary. Hands up. Who would think that? So, in this presentation, I will show you how that is actually the truth, that is made, at least partly, here in Budapest, in Hungary. So, before I get to that, let me just start with a very brief introduction. I am István Ráth, I'm the CEO of IncQuery, and IncQuery is actually a university spin-off from this very university. We started about 11 years ago, and the mission of the company is to help engineers, be it mechanical engineers, electrical engineers, software engineers, systems engineers, have an easier way of getting their job done faster and more efficiently. So we focus on engineering tools, and we work in several industries like automotive, aerospace, biomedical, many others. And what we really want to achieve with all of our research and development work is really to make sure that engineering work gets done better and more efficiently. So over these 11 years, we've been fortunate enough to work all over the world with many companies from the US, Canada, Europe, Asia, you name it. And in particular, we've been doing a lot of work in the aerospace and defense industry. And of course, you can see on the slide here that one of our headline customers or major clients has been for more than 5 years now the Jet Propulsion Laboratory over in Pasadena, California, from where Robert is also from. So this is going to be actually the focus of my presentation for today. So, as Robert has explained to you, he's been working with a special division inside this organization called Computer Engineering, Aided Engineering, or CAE division. And these people are actually a group of experts who are focusing on providing software ecosystems for many different kinds of engineers who work in that organization, like mechatronical, electrical engineers, system designers, and many others. So lots of people inside the Jet Propulsion Laboratory depend on using the ecosystems and the platforms that this division is maintaining to get their day-to-day work done. And so you may remember Robert's slide on the Dragon architecture, which is quite a high-level overview of how this software ecosystem looks like internally. And if you pay very close attention to that slide, it's a little bit hard to see on the screen, unfortunately. There is a box with the label IncQuery inside. So that's actually the piece that I'm going to be talking about today that is made here in Budapest and they use to make things fly. So what is IncQuery? What is our vision? IncQuery, what we created over the last 10 years, is a new platform for digital engineering automation. So this is the key enabler to help engineers get their work done faster and more efficiently. There are three main ingredients to our vision from a technological point of view. We do quality assurance solutions, what we call automated quality gates, to detect and remove errors from engineering work. We also do so-called handover automation components, which automate a lot of the manual work that Robert was talking about before, involved in using the combination of tools together, so moving information from Excel to an architecture design tool or back and forth. And finally, we also built very important foundational technology, actually originally back at the university, that we call the digital thread analytics engine that can help us work together with a lot of different tool ecosystems that are actually in place in the architecture at organizations like the Jet Propulsion Laboratory. If you remember Robert's slides, he has been giving us a very thorough overview on the overall high-level picture of the workflow that they follow when they design a product, such as the Ingenuity helicopter or the Perseverance rover. And in the middle, he has focused on the architecture design and the quantitative analysis part. And in fact, our products related to the quality assurance field are very much focused on exactly this area. So in order to understand how this works, let's take a step back and understand a little bit the context, So first of all, Robert has mentioned the field of model-based systems engineering. This is in fact a very important discipline. Originally, or historically, it actually originates from NASA. From back in the 60s, systems engineering was developed originally as part of the Apollo program. And over the decades that have gone by since then, this has gradually evolved into a discipline that is supported by more and more digital tools nowadays. So as Robert has said, now what we are witnessing in the industry is kind of a paradigm shift from this traditional method of systems engineering towards using formal languages, automation solutions, requirements capture, architecture design, and all the rest. Usually, the central notion that you have to understand when you talk about MBSE is a systems modeling language, which is used to capture the design. And sometimes it's also used in combination with other software engineering-related methods as well. Just to give you a very brief glimpse into this world, I included a couple of screenshots from some of the most popular MBSE tools that are on the market today. This is the CATIA No Magic solution, as it used to be called Magic Draw. I'm sure some of you may be familiar with this. This is actually a dominant player, especially in the US market today. So majority of aerospace companies like Boeing or Lockheed Martin or Airbus even are going to be using this tool to support this discipline. There are also other commercial tools as well, like Enterprise Architect, which are quite popular in other industries, such as the automotive industry over here in Europe. There are open source solutions readily available, like the Capella from the Eclipse ecosystem. And finally, there are new generation tools appearing on the market, which take advantage of the newest innovations in the cloud and web-based domain, also incorporating some AI aspects as well. This is a brand new solution from Siemens called the SimCenter. So, back to my original point, I was talking about quality assurance, but what do we actually mean by engineering quality? It's very important to understand as well, but it's actually not that hard. There are three key ingredients to engineering quality. Making sure that our work is free from common mistakes, also making sure that the work complies to various relevant standards that are used in the industry. And finally, and perhaps maybe that's the most critical and difficult to capture well, is to make sure the work also corresponds to a methodology that is somehow inherent to an organization. From a technological point of view, we can see that the common mistakes are relatively easy to spot, and that's why it's actually supported by many of the tools that I've been showing to you previously, and you can also find similar features and solutions in some of the other commercial vendor solutions as well, be it documentation management, issue tracking, simulation software, or product line and requirements capture. So this is relatively easy to do. What is a little bit harder to do is the standards conformance. And when I talk about standard, I do not only mean the standard, as Robert already mentioned, like the system modeling language like SysML or Modelica. There can be also very important, especially safety-related standards at play here, like the ISO 26262 or SIL, or domain-specific standards like AUTOSAR for the automotive industry. And this is a little bit harder to do from a technological point of view to assess whether a particular design or an engineering document is fully standard compliant. But what is the hardest, as I said before, is the methodology part. Methodologies in this engineering space are often captured or described in documents, books. Some of them are actually pretty popular and widespread in use. But these describe how engineering work should be done on a very high level, in a very human-like way. So to translate that into something that can be checked by a quality assurance tool is really the hard part. And this is what we set out to address with our products. Why is it so important to manage quality in an engineering process? The simple answer to that is one word: collaboration. It's because of the fact that engineering work is not done in an isolated way. It's actually done by collaborating groups of people who need to exchange their work with each other, who need to collaborate to the same thing. So that's why it's very important to make sure that everyone's output, everyone's work can correspond to the same quality standard. There is a notion that we introduced that expresses this desire, which is called model governance. Model governance is, simply put, the set of quality criteria that are pertinent to define the precondition for data exchange in engineering workflows. These workflows are actually often described using the V or the Y model that some of you may be familiar with. That is a very common and recurring pattern employed by industries like the automotive or the aerospace industry, which prescribe the adherence to very strict quality standards. So when we talk about model governance, what we really mean is that we want to make sure that all the engineering work, or the models in our terminology, are consistent in style in terms of standard conformance. They are understandable across several teams when we are talking about collaboration. So they have a methodology conformance property. And finally, they are free of common mistakes and anti-patterns, and of course, complete. There is nothing missing. Everything is there to make sure that the helicopter can fly. So the product that, for example, is also used by NASA, but some other companies as well, is focusing to implement this principle, especially on the left side of the V, so focusing on the integration or the interplay between requirements capture, system design, and component design. So now, let's put this into a little bit more specific terms to show you some screenshots how this technology actually looks like from an end user's point of view. I put here a very simple example for what can be considered a common mistake, but also actually as a methodology conformance issue from a certain point of view. This is how a quality gate or a quality assurance can actually look like when it's running inside an architecture design framework or platform like the Enterprise Architect from Spark Systems. This is a very simple digital twin for that matter. It's actually a model that describes behavior in terms of a state chart or an activity diagram. And when we define or capture the desired behavior of a system using such a language and these tools, it's very important that we make sure that our work is complete. There are no missing parts of the model. In this case, we are looking for guard conditions that are necessary, in Robert's terms, to make sure that whatever we do in our engineering environment can support the repeatable and executable representation of the system and its different levels. So we need to find such mistakes in the engineering model to make sure that our work is free of basic mistakes, and it can also make sure that it adheres to methodologies that describe that this should not happen in our real world. Here on the bottom of the slide, you can see a pointer to that particular methodology, which is actually at play here. So when we finally put this into an actual deployment, like the one at the Jet Propulsion Laboratory, the architecture that we end up with looks something like this. This is actually an instance of that engineering environment that Robert was talking about. Here we have a combination of engineering tools like Jira, Teamwork Cloud, OpenMBE, JAMA, and Modellon. These are all off-the-shelf components. They are all connected together technologically by an integration bus, which is provided by OpenMBE. That's a digital thread platform or a tool integration platform. And our quality assurance product, IncQuery Validator, plugs into such a platform, and it can automate the quality assurance process by automatically running these quality-related checks whenever an engineer changes something in their work. Whenever a new version of an engineering model or a document is committed to the repository, it works very similarly to quality assurance products that you are all familiar with from the software engineering world, basically very analogous to a source code checker, but this one doesn't look at source code, it looks at the model, it looks at the digital twin specification, so to say. It can produce a report that will give you an overall indication as to what are the problems which are in the project, and of course it can also compute an overall quality metric that will be very useful by a manager or a stakeholder in the organization to assess whether there is a problem that needs to be assessed. These things are very, very important because when we are talking about a project like the Perseverance or Ingenuity or some others, it's very important to identify and catch such design mistakes as early as possible. Why? Because if we don't do that, and if we only rely on a field testing, or worse yet, actual deployment over in space, and there is a mistake that will surface, it's very, very hard and expensive to fix. In the case of NASA, it's extreme. You cannot really debug a rover on Mars, or it's very hard to do. But in industries like automotive or aerospace, it's also very, very expensive. Think of, for example, the troubles that Boeing is going through in recent days. This is just the most simple incarnation of such a tool or such a technology. There are much more advanced and sophisticated environments which engineers interact with such digital twin pipelines. For example, the Jupyter framework. Who here is familiar with Jupyter? Who has seen Jupyter notebooks? That's actually a very, very useful skill, and Python in general, if you want to work at a place like NASA. So I recommend everyone to learn Jupyter and Python. And finally, as a closing thought, for those of you who have an inclination to do some research or are interested in R&D work, we do not only have an industrial collaboration, but also very strong ties to the academic world still, since we come from this university. In particularly, I would like to mention our collaboration with the Critical Systems Research Group in this faculty. Over the last 3 years, we've been working at industrializing their model checking technology as a collaboration between academia, practitioners, and commercial vendors. And it was a very successful collaboration because we actually managed to do model checking on behavioral models which are used by these aerospace systems. So there is some paper and some information on the internet as well. In case you are interested, I recommend you check it out and see how it can work together already at the university research level to do such a collaboration. This is in fact very closely related also to the safety analysis use case that Robert has mentioned in this presentation before. It's basically the same idea implemented with real technology. So, in summary, I would like to repeat what Robert has also concluded with, that right now, this industry is going through a very significant strategic shift towards the digitalization. And within this space, the areas of particular interest are formal methods, languages, automations, to realize things like digital threads, quality assurance, and other solutions as well. This is all of essential importance, especially in industries like automotive, biomedical, aerospace, defense, and energy, because There, we need to provide a way to achieve systematic qualification and audit training to finally close the gap, this productivity gap that exists between the old way of working with document-based methods and the new way of working with software and models. And of course, everything should be implemented in an open way that is extensible so that small vendors like we can participate in large ecosystems and provide solutions like this one to NASA. And it's also very important because this enables the collaboration between academia and practitioners and vendors like we have. So the biggest perk of my job personally is to travel and to do some customer visits. And in this particular case, this was actually a realization of a childhood dream that I got to do twice, to visit JPL in Pasadena in California. The spacecraft that you can see on this photo in the background is the Europa Clipper mission. Who here is familiar with what Europa Clipper is? Europa Clipper is a spacecraft that is going to launch this year and is going to orbit the moon Europa and to collect some samples for analysis to assess whether there is a chance of life in the ocean that is suspected to be on that moon. So we got to see that in person. And if any one of you would be interested in joining us and doing customer visits like this and working on very interesting engineering tool technology, then please feel free to reach out and talk to me. I'm very open to answer any questions. Thank you very much.
Thank you so much. The first question is, what was the key to success in your collaboration with academia practitioners and vendors?
That's a very, very good question. I think the key to success is to have an open mind, always. Usually, the collaboration from an industrial point of view with academic partners is a challenging one because the kind of problems that industrial companies have are sometimes a lot simpler than what academic people think they have. So the key to that is to have an open mind and to have an open eye for finding the right match between the organization and the solution that a research organization can have. And this is where we, for example, can come into the play as a kind of a catalyst.
Thank you. Next, what advice would you give to aspiring system engineers?
To learn Python. For real.
Thank you. Next is, do you think SysML v2 will speed up the paradigm shift to MBSE?
I hope so. SysML v2, for those of you who don't know, is a new generation of the systems modeling language, this international standard, which has been elaborated over the last 5 years and released just now. And there is a big hope in the industry that this will accelerate this commoditization process that Robert and I have been talking about, because it liberates these ecosystems from the hold of strong commercial and big vendors.
Thank you so much.
Okay, thanks again.